Hello everyone, welcome to this year physics session. So unfortunately we had some glitches in the past week. We're supposed to have had this tutorial session on Thursday, but nonetheless we're just gonna go on with it and look at sound waves and Doppler effect in today's session. So I'm not gonna waste much time. I'm just gonna start with question 9, which is the question showing on your screen right now. So if you are live and joining us either via Teams or on the YouTube platform, you are welcome to share your comments, to ask questions, and interact with us as we are live here on Yebo Physics today. So our first question is a question on Doppler effect, and with the Doppler effect, we generally have our master equation, which relates the frequency observed to the frequency from the source through the expression V plus V naught. Okay, I think that's rather too thick. Over V minus Vs. So this is the velocity. V is the velocity of the sound. Velocity of the sound waves. Remember, we're dealing with sound. Vo is the velocity of the observer. So remember, we've got the observer. And Vs will be the velocity of the source. So we have the source giving off a sound of a certain frequency and the observer observing that frequency. So this F becomes the frequency of the sound from the source. So there is a change. This is the new frequency that is observed whenever or if ever the observer or the source are moving either towards or away from each other. So if the values of V or and or Vs are positive, so positive values means we are moving towards the observer or they are moving towards each other, either way. So it's the source moving towards the observer or the observer moving towards the source. Then if the values are negative for both VO and or Vs, then this is when they are moving away from each other. So this effect is basically a case whereby when a source is moving towards the observer, basically it tends to result in an increase in the observed frequency. So even if the observer is moving towards the source of sound, the frequency tends to increase. So you would think of it as, let's assume you have, okay, let's talk of a boat. Let's say these are ripples that are coming towards a boat at this point, right? So if the boat is stationary, then at equal intervals of time, you can see the wavelength there will be the same. The wavelength will be the same throughout the process, but as the boat begins, when the boat begins to move towards uh, towards the waves, we will tend to see the time between the coverage of the wavelengths becoming small. So T reduces, and when T reduces, frequency will increase. So this is basically the interaction between the boat and the successive crests. If the boat is moving towards the source, so let's say we forgot our source, which is the vibrator at that point, then what then happens is an increase in frequency because we are reducing the period by which we experience those crests. So the opposite will happen when the boat is moving away from this source. So this is basically how we are going to use this master equation for our Doppler effect. So I'm just going to go to the question so that we can see what answers we get with these examples given here. We've got our first one, which is a truck moving at 36 meters per second. So this is the velocity of the truck, which passes a police car moving at 45 meters per second in the opposite direction. So already there's a sense of these two coming close to each other. So this is towards, we're going to use positive values here. If the frequency of the siren relative to the police car is 500 hertz, what is the frequency heard by an observer in the truck as the police car approaches the truck? So this is the frequency we need to calculate. And we've got the velocity of sound plus the velocity of the observer. And the observer, in this case, the observer is in the truck, by an observer in the truck. So that's the velocity of the truck plus all over V minus Vs multiplied by the frequency of the sound, which is initially given as 500 hertz. So we have the speed of sound needs to be taken to be 343 meters per second. So we have 343 plus the velocity of the observer is the velocity of the truck, 36 over 343 minus 45, which is the velocity of the police car, and the frequency of the original wave is 500. So if we go through that calculation, the expression there simply gives us a value of 635.9, 635.5.9 hertz. So this becomes the observed frequency, and that will give you a 636 if we are to round it to 3 significant figures. And 636 is B, which should be correct. Okay, so that's how we deal with that part. The second part is still related. It considers the same case where we have a truck and a police car, and the speeds are still the same, but the question is only different in the sense that we need to find the change in frequency in hertz heard by an observer in the truck as the two vehicles pass each other. So which means we have a case whereby this is the frequency observed as the police vehicle approaches, or as the vehicles approach each other, but we need to also find the frequency after the two vehicles pass each other. So what that means is our delta F, the change is always final frequency minus initial frequency. Or otherwise we'll find the absolute value. If that gives us a negative, that is not a problem. But anyway, our final frequency is after the two vehicles pass each other, and we say the new frequency will be V. Now remember, these are moving away from each other, so we now have minus V observer over V plus V source. We've just opposed the signs because remember what we said here. If the two are moving away from each other, then we have negative values for VO and VS. So if we apply negative values there to the initial equation, that is what we should get. And therefore we have 343 minus 36 over 343 plus 45. Everything multiplied by 500. So I'm just going to change a few things in the expression, which is basically changing the sign in my initial calculation and nothing else. Then what I get there is 395. So we're seeing that as the two vehicles are moving away from each other, the frequency is less than the initial 395.6 hertz. So this is what we described in terms of the example with the boat, where we say the frequency is higher when they move towards each other. And when they move away, it's the opposite. So it takes time for the boat to experience, a longer time for the boat to experience the effect of the two crests. So therefore, the calculation of delta F, the change in frequency there, is 395.6, or let me call it 396, minus the one that we got earlier was 636. So 396 minus 636, that's negative 240 hertz. So the negative simply means the frequency decreases by 240 hertz. So the change is 240 hertz, which we see here in C. So we have a 240 hertz change in frequency when the two vehicles pass each other. Now, another interesting one. This is dealing with sound. It's not really on Doppler effect, but it's on sound level. We say is by what factor is the intensity of sound at a rock concert louder than that of a whisper when the two intensity levels are 120 decibels and 20 decibels respectively. So remember our formula for sound level in dB is 10 log I over I naught. I naught is the reference which is measured at the lowest audible level, which is 1 times 10 to the minus 12 watts. So that's watts per square meter for intensity. So the 1 times 10 to the minus 12 watts per square meter. So in this case, this sound level, we're told that we will need to find by what factor the intensity, which is this intensity of sound, is louder than that of a whisper. And the ratio there for the sound levels are 120 and 20 decibels respectively. So one way to look at it is to say, let's say the I for the rock concert, we'll call it IR, and I for the whisper, we'll call it IW. So we've got, we want the ratio of IR to IW. So how do we get that ratio? We know that we have the level 120 is equal to 10 log I for the rock concert over I naught, and 20 is equal to 10 log I for the whisper over the same I naught. So if, because this is on a decibel scale, 120 minus 20 gives us 10 log IR over I naught minus 10 log IW over I naught. So we can, we get 100 there, we divide by 10, remove that part. What we have is 100 over 10, so we remain with 10 equals to the log of IR. Remember what we want is a ratio, IR over I naught, and because the logs are subtracting, we can divide this by IW over I naught. We now have that ratio that we wanted, which is IR over IW. So to eliminate the log, we have to raise everything to the power of 10. So 10 to the that and 10 to the that. Then that means 10 to the 10 is equal to, what remains inside there is IR over IW. So because this eliminates. So that ratio is simply 10 to the 10. And this is what we see in D. Another interesting way to look at it is we have 120 dB, and compared to 20 dB. The difference between these two levels is 100 decibels, which is the same thing that we have there. But we know that each time we increase power by a factor of 2, this is a level that we call a 3 dB change, right? So every 3 dB change is like a double up of power. So which means we can find how many times we are doubling this power in a difference of 100 decibels. And that gives you 33 times. So which means you have 2 multiplied 33 times, and this is 2 to the 33, and you want to express this as 10 to the x. So that means 33 log 2 will be equal to x log 10. Log 10 is 1. So our answer is basically x equals to 33 log 2. This is basically a very close estimate. So we'll see 33 log 2 gives us 9.9. 9.9. So our x is basically 9.9, which means that the factor there is 10 to the x, which is 10 to the 9.9. That's 10 to the 10. So it gives us the same answer as what we got from there. So that's the comparison between the two, and yeah, we can move on. Number 12, we can pass. There is no question on 12, no question on 13. We will just go on to number 14. Number 14 says, do not try the following, because this is a dangerous experiment to try. So it's not advisable to try this at home. This question is only about a hypothetical possibility. If you were standing below an object emitting a frequency of sound, a frequency sound falling at terminal velocity. So the object is falling at terminal velocity and it's emitting a certain frequency. As it approaches you, would you hear the sound drop in frequency, stay the same, increase in frequency, decrease in loudness, stay at the same loudness? So how would we conceptualize this? We've got an object falling at terminal velocity and it's giving off a sound of a certain frequency, fixed frequency. So fixed frequency, terminal velocity. Where did I see terminal velocity there? So the sound is emitted at fixed frequency. The object is moving with terminal velocity, and you are the observer at a point below this falling object. What would you pick or observe from this frequency or from this sound in terms of its loudness? Anyone? So I see we don't have anyone joined so far on YouTube. I don't know about Teams. But it's okay. We should look at it this way. We have a velocity that we're saying is constant. Remember, when we are looking at the shift in frequency, we are looking at the movement of the source towards the observer or the observer towards the source. And this is where the shift is. But now this situation, we are given a situation whereby the frequency already being observed by the observer is based upon the movement of the falling object, which is already a shifted frequency. So because the movement is not an acceleration, this is terminal velocity, there's no change in velocity, the observer will continue hearing the same frequency, which is the frequency shift that we calculated earlier using this expression, right? So whatever the source frequency is, this object is already, we have a stationary object, it's 0, but the source is coming towards the observer with terminal velocity. So whatever frequency is being observed is always the shift in frequency, and it will be constant because the frequency source is fixed and also the velocity of the source is a terminal velocity, which is constant. So there is no change in frequency from what the observer is gonna experience. There's no drop, there's no increase, it stays the same. So B is the best answer in this case. So it's also an application of your understanding of terminal velocity and also picking the information given from the question which says we have got a fixed source. So you apply that to the same expression, our master equation which we introduced when we started, then you find the frequency is gonna remain the same. Okay, then if a plane is flying at a speed so that the apex half angle of its shockwave is 30 degrees, what is its speed if the speed of sound is 320 meters per second? So this is quite an easy one. Remember, this is based on shockwaves. You have a system that is moving at a certain speed, and that speed is basically related to the speed of sound. So you talk of Mach 2, you're saying you're moving at twice the speed of sound. Mach 3 is 3 times the speed of sound. But this apex is basically the angle given by an object that's moving in that direction, and with its speed given by sine theta is equal to the speed of the object over the speed of sound. Actually, no, sorry, it's actually the speed of sound. In this case, speed of sound over speed of object. How do we put that? Speed of object over speed of sound. It's the other way around, right? Speed of sound over speed of object. Yeah, something like that. So in this case, we are told that the angle is 30. So we have sine 30 is equal to the speed of sound Vs, which we are given as 320 over V object. And we know sine 30 is 1/2. So we've got 1 over 2 equals to multiplied by V naught equals to 320. Multiplied by 2 both sides, we get V naught equals 320 times 2. That gives us a speed of 640 for this plane, 640 meters per second. So it is Mach 2, which is twice the speed of sound. So that's the relationship that you need to know. That's the relationship that you need to know with regards to this, with regards to the issue of shockwaves. So it's basically a shockwave that is created when an object moves through fluid like that. Okay, I need to fix something on the screen. I don't know what happened to my tablet. Okay, it's probably all right. So I think maybe if you did, in case you didn't see what was going on here, it was just a glitch on the screen. We have an object that is moving at a certain speed through sound, right? And we are saying if the velocity of that object, in this case is an airplane, is not known, we can know from the angle, which is the angle of this cone that's created whenever we make a drawing or a sketch of how the speed or how the object is steering through the fluid or through the air like that. So in this case, we are saying if an object moves at twice the speed of sound, we call that Mach 2. If it's moving at 3 times the speed of sound, it is referred to as a Mach 3 kind of speed. But what it means is it will form a cone, a sound cone, which looks like that and has got an angle theta, which is related to the speed of the sound with respect to the speed of the object. And in this case, we are told that the cone angle is 30 degrees and the speed of sound is 320 meters per second. So we need to find the velocity of the plane that results in such a cone angle. Hence, we did the multiplication. The working there is sine 30 is half, and half is equal to 320 over V naught. So that means V naught becomes 640. It is twice the speed of sound. So that's that's it with this part of the question. We have 640. The last part should be question 16. So I'll be finishing. Lishan is gonna come in anyway and finish the rest, guys. So please forgive me. Right? It is possible to hear an approaching train before you can see it by listening to sound wave through the track. If the elastic modulus of is 2 times 10 to the 11 Newton per meter squared and the density of steel is 7.8 times 10 to the 3 kgs per meter cubed, approximately how many times faster is the speed of sound in the track than in air? So it's always nice. We always have formulas given to you, even through in your question papers. Some formulas are given. If you are looking at sound through a string in tension, you have T over mu for the velocity of that sound. Now we're looking at sound through some bulky material, and this is given by the bulk modulus of the material over the density. So it's the elastic modulus, so it's always the property at the denominator, and it's always the measured quantity, which is which relates to the force in the numerator. So if we take the square root of that, we are simply referring to a square root of 7, 2 times 10 to the 11 for the elasticity modulus, divided by the density, which is given as 7.8 times 10 to the 3. And the velocity we get there should be the square root of 2 10 to the 11 over 7.8 10 to the 3. 5063.7 meters per second. And how many times this is to the speed of sound? The factor is V over Vs, which is 5063.7 over 340 meters per second. The factor has no units, so divide everything by 340. We get 14.89, which is 15 times. So the sound moves 15 times inside the track than it would move in air. And there we are, we have 15 there. That should be fine. Okay. So let me see. Okay, so guys, that's about it for today. I'm just gonna leave it to Lucian. Is gonna take over from the questions that are remaining for today, and we'll be continuing in the coming few days with the next set of questions until we get to the end. So keep on studying, keep on getting in touch with us. If don't lag behind too much, you need to always be up to date with regards to your studies and to the information that you need to know, and as you get ready for your coming exams. Otherwise, from me and everyone at Yebo Physics, goodbye and have a good day.